Hello everyone, welcome to the RCNP course. At this part, we're going to introduce the root redistribution. About the root redistribution, firstly, you should know that nowadays, networks are typically designed or planned to use one routing protocol to reduce the network complexity and improve the maintenance efficiency. However, in some cases, multiple routing protocols may be used to implement transmission from an old network to a new one, or intercommunication between organizations. Root redistribution rises in response to the need of allowing networks with different protocols to communicate with each other. So about the root redistribution, let's see the overview of it first. A multi-routing protocol network runs two or even more routing protocols at the same time. Or in some cases, even they're running the same routing protocol, but the process ID is different. So we think actually there are two different processes, two different routing protocols. For example, let's see some cases. First case, R1 cannot learn the root information in the OSPF domain because R1 is running OSPF. And R3 cannot learn the root information in the ISS domain either because it's only running OSPF. Right? R2 can learn all the routing information using ISS and OSPF because on R2, we are running both ISS and the OSPF. However, OSPF and ISS processes are separated. The processes are separated actually when we check the routing entries, you should know that on R2, actually there are two protocol routing table. One is the ISS routing table, another is the OSPF routing table. So even some of the entries in these two routing protocols are enabled or can be found in the global routing table, but actually they will not exchange the entries. This is the first case. And when you check the routing table, you can find on R2, both of these protocols routing entries can be found, but on R1, you can find the ISS routing table. On R3, you can only find the OSPF routing table. This is the first case. And the case two, as a gateway of the internal network, R2 is configured with static route to the external network. The internal network runs OSPF, but since we configure the static route on R2, and R1 will not get the route to the external, actually, will not get this static route because between R1 and R2, what we are running is OSPF. And by default, OSPF cannot carry the route. And by default, OSPF cannot carry the static route. Right? So R1 cannot learn the static route on R2 by default. If you check the routing table, you can find on R1, we cannot find the static route on it. And this is a problem when we use the static route. So root redistribution allows border routers to exchange and advertise routing information between root protocols, thus connecting different routing domains. For example, we can redistribute from one protocol to another, or we can redistribute between multiple instances of the same protocol. Right? For example, from the dynamic routing protocol to another dynamic routing protocol, from a static to the dynamic, or from the direct route to the dynamic. Right? This is called root redistribution. Actually, root redistribution is using some commands to manually exchange routing entries between different routing protocols. Okay. After knowing the principle, next, let's see some application scenarios. The common routing protocols usage is like this. We use static routes at network egresses and in areas with high security requirements. While we use OSPF or ISIS for some small or medium-sized networks, and the RIP for small or outdated networks. And we use BGP for large networks and ISS for operators' backbone networks. It's application of different types of routing protocols. And when you design a network, you should choose which protocol you use based on the maybe real scenario. And next, let's see the route redistribution usage. It can be used to introduce static or direct routes into dynamic routing protocols, or merge organization networks running different routing protocols, change the routing protocol to another one, or on a large network, the backbone network runs BGP. Organizations at the edge runs OSPF. And OSPF is responsible for calculating route entries. BGP is responsible for transmit these entries calculated by different routing protocols. So you must have a tool that can maybe exchange or that can transmit the routing entries calculated by OSPF to BGP so that BGP can maybe transmit or share these entries with others, right? And the tool we just mentioned is called route redistribution. And after knowing this, next, let's see route redistribution principle and the configuration. First, we use multiple routing protocols only when necessary. Because if we use multiple routing protocols, it's very complex, no matter for a network implementation or network maintenance. So only when it's necessary, you can use the multiple routing protocols. And for the routing protocol planning, we should maybe connect the edge networks to the core network, redistribute the IGP routes into BGP. This is what you should take into consideration during the planning. And next is the redistribution point. About the redistribution point, you can think about the cases we just introduced, right? On the left is ISIS, on the right is OSPF. So the router which are connecting these two protocols, or the router which are running both of these protocols, you can think it's a redistribution point. And based on different networks, it could be a single point connection or multi-point connection. If it's a single point connection, it's quite easy. You just need to redistribute maybe routes between different protocols on one point, on one router. Or if it's a multi-point connection, it's a little more complex. Except the route redistribution, you should think about after route redistribution, if it will cause loops or not, right? And in the following content, we will have some cases to introduce the loops that will be caused by the route redistribution and how to solve these problems. Okay. And next, let's see some cases. The first case is unidirectional route redistribution. Means we just need to redistribute the route from the edge to the core network. But we don't need to redistribute the route from the core network to the edge network. This is called unidirectional route redistribution. It's quite easy to understand. Except that another type is called bidirectional route redistribution. In this case, R1, R2 is running OSPF, ISIS. In this case, R1 and R2 are running ISIS, R2, R3 are running OSPF. And to exchange the route information between ISIS and OSPF, so on R2, we should do the route redistribution. The reason why we call it bidirectional, because we should redistribute the route from ISS to OSPF, and we should redistribute the root entries from OSPF to ISIS. Right? This is called bidirectional. So to do the root redistribution, no matter it's a unidirectional or bidirectional, we said that we are manually using some commands to exchange the routing entries. So here, let's see the command we use. For OSPF, router OSPF1 redistributes followed with the protocols which are calculating the root entries we want to redistribute and the subnets. Of course, you can change the metric type, or you can refer to some root maps you have already configured. And for RIP, the configuration command is router RIP redistribute followed with different types of protocols, and you can also change the metric, or you can also refer to the root map. Okay. But for this configuration, you should know that the direction matters to root redistribution. If you want to redistribute the root from OSPF to ISIS, so you should use the command in the configuration view of ISIS. If you want to redistribute from ISIS to OSPF, so you should configure it in OSPF configuration view. Okay, the direction matters. And the router implementing root redistribution does not change its local routing table. You can think about it. If we do the root redistribution on R2, and R2 is running both OSPF and ISIS, so without root redistribution, R2 has already mastered all the routing entries generated by OSPF and ISIS, and will install them into the routing table. So no matter if you redistribute or not, it will not affect or not change local routing table. And only routes in the routing table can be redistributed, because only the routes in the routing table take effect. Okay, after knowing the commands, next let's see some examples. Okay, now in this case, what we should do is to redistribute the RIP routes into OSPF and the OSPF route into RIP. So let's see the command here. On R2, firstly, router RIP means we are configuring RIP. And so it represents that RIP is the destination protocol. We are redistribute OSPF into RIP, redistribute OSPF 1. Here, 1 is the process ID. So after using this command, the OSPF routes has been redistributed into RIP, as you can see in this figure. And except that, we should redistribute RIP into OSPF. So router OSPF1 redistribute RIP subnets. So in this case, RIP routes has been redistributed into OSPF, and it will become the OSPF route. Okay, OSPF route. And next case, on R2. On R2, it has static route and direct connect routes. So if we want to redistribute these routes into OSPF, firstly, let's see the configuration. Router OSPF1 default information originates, redistribute static subnets, redistributed connected subnets. After using these commands, the result is like this. All these three routes has been redistributed into OSPF and it becomes OSPF routes. But I think it's very easy for you to understand these two commands, redistribute. But what's the function of this command? Default information originate. Because in this case, actually, there is a special route, which is called the default route. And if we want to redistribute the default route into OSPF without this command, actually, it will not take effect. Default information originate. So you should pay attention. You should remember it. When you redistribute or when you import some default routes into OSPF, it's necessary to use this command, or OSPF will not generate the default routes. Okay. This is a configuration in this case. And next, suboptimal routing caused by route redistribution misconfiguration. Let's see. Now, this is a multi-point route redistribution, right? We can do the route redistribution on both R2 and the R3. And let's see the configuration here. On R2, redistribute the RIP to OSPF. You can see here, from RIP to OSPF on R2. And then after that, firstly, on R4, there is the route 4.4.4.0. And about this route, since both R4, R3 is running RIP, so R4 will send it to R3, and R4 will send it to R2. On R2, we have redistributed it into OSPF. So it becomes an OSPF route, and the R2 will send it to R1 because they are running OSPF. And of course, R1 will send it to R3 actually. So in this case, we can find R3 has received the routes. How can I say that? So in this case, R3 receives two routes to the same destination. One is from R1, another is from R4, right? Two different routes reference two different paths. So R3 should take it into consideration. Which path or which route is preferred? You can see. R3 receives the route to 4.4.40 from R1 and R4 at the same time, while R3 choose R1 as the next hop. You should think about why. Because from our point of view, we think we should choose R4 because R4 is directly connected. But why R3 choose R1? Because to the same destination, this is an OSPF route. This is a RIP route. And OSPF has a higher priority than RIP. If R3 choose this route from R1, let's see how does the traffic forward it. After, for example, this is the PC, and it sends the packet to 4.4.4.0. After receiving that, R3 will send it to R2, R2 send to R1, R1 send to R4. Actually, this is the not the optimal path. Okay. This is the problem that caused by the misconfiguration of route redistribution. Okay, and next, let's see route policy principles and configuration. Because to solve these problems, we just introduced caused by misconfiguration of route redistribution. We can use the routing policy to solve this problem. Let's see how that works. Routing policies can be used together with route redistribution to filter specific routes or change route attributes. Route match tool is the ACO and the prefix list. ACO, I think you are very familiar with it, right? It can be used to match packets, or at the same time, it can also be used to match the routes. And another tool is prefix list. And later we will introduce what's the prefix list and the difference between ACO and prefix list. Okay, next is the tool for modifying a routing policy. It's a route map. So the difference between them, or the relationship between ACO and route map, is that ACO and prefix list are the lure. ACO and prefix list are the tools which can be used to match the objects, while route map is the tool to define what we do to these matched objects. Okay, it's a relationship between them. Now, in this case, we should do the redistribution of R2. And during redistribution, route maps are needed only for redistributing 192.168.3.0 from OSPF to RIP, right, in this figure. So we should have a tool to match 192.168.3.0. And then we should use the root map to apply some policies to it. Okay, so let's see the configuration here. The root map application scenarios include root filtering or policy execution during root redistribution, or policy-based routes, or nets, or policy deployment in BGP or some other cases. It's used very common in the network. And the steps of configuring a routing policy use a route map is shown here. Use an ACL or a prefix list to match the destination routes. Invoke the ACL or prefix list in the route map, change the route attributes, configure the redistribution command in the root protocol, and invoke the route map. Okay, this is the steps for configuring. And let's see some cases here. Using an ACL to match routes. R1 redistributes the route from RIP into OSPF. By default, all RIP routes are injected to OSPF. While if you don't want to inject the specified routes into OSPF, filter out the routes. Let's see how to do that. If we want to match the 192.168.1.0/24, if we want to match this route, we can use the standard ACL. Access list 1 permit 192.168.1.0. So in this case, we can match this route, but actually it has some shortages because standard ACLs can only match routes by network ID, but cannot control the prefix length. So after using the ACL, you can see access list permit 192.168.10.0, access list permit 192.168.11.0. For these four routes, which of them can be matched? Right, is the route 3 and route 4. So by using ACL, we can match some of the routes, but it has some shortages. Each route requires a standard ACL entry, and wide range matching is not supported by using the standard ACL. So to solve this problem, we can use the extended ACL, and let's see how that works. Now, we want to ensure that the route we match, which network ID is 192.168.1.0, mask length 24. So let's see how to do this. We use the extended ACL, access list 100, permit 192.168.1.0, 0.0.0.0, and 255.255.255.0, and 0.0.0.0. You can find here this part 192.168.1.0. This is the network ID of this route. And here 255.255.255.0. This is the mask length of this route. So by using extended ACL, how to control this? Actually, we use the wildcard here. 0.0.0.0 reference, it must strictly match. Strictly match means it must be the same. So in this case, we can control that the network ID must be the same as this 192.168.1.0, and the mask must be 255.255.255.0. Okay, so the extended ACL matches network ID by source and the mask by destination. It's a little different from the application of the extended ACL, which are used to match the packets, right? You should know this. So if we want to match these two, route 3 and route 4, by using extended ACL, the configuration is like this. Right? Okay, this is about the using of extended ACL to match routes, but it also has some disadvantages. An extended ACL entry can be used to match routes with consecutive network IDs. However, mask must be the same. Otherwise, multiple entries need to be used for matching. Okay, this is about the ACL. Next is the prefix list. Firstly, let's introduce this tool. A prefix list uses network IDs and prefix lengths to match roots, improving matching accuracy. So by using a prefix list, we can control the network ID and the prefix length at the same time. A prefix list contains one or more entries. Entries are sorted out by sequence number, which is similar to ACL. And if a root does not match any entry in the prefix list, it will not be redistributed. So let's see some case. Firstly, this is a configuration of the IP prefix list. IP prefix list. You should set the name, prefix list name, and or you can use the sequence number, right? And then deny permit. This is the action. And IP prefix. You set the IP prefix here, the network ID, and the last two parts are used to control the mask length. The GE represents the greater equal, greater equal, and the AOE means less equal. For example, greater equal 22, less equal 23. So the mask length could be 22 or 23. It's used to limit the mask length. And let's try to read this prefix list. IP prefix list, Ruijie, so the name is Ruijie. Permit 192.168.0.0/16. This is the prefix must be 192.168. Since /16 means the first 16 bits must be the same. So it represents that the root we match must start with 192.168 dot. And the following part can be any numbers, right? And next, GE 24, LE 26 means greater equal than 24, less equal than 26. The mask length will be 24, 25, and 26. So you can see here, first 16 bits of the roots to be matched means it could be 192.168. And greater equal 24, less equal 26 is the control of the mask length. After knowing this, let's see how to use a prefix list to do the control of the matched roots. Now, the prefix list is like this. IP prefix list Ruijie sequence 5 permit 192.168.10.0/24. If we use this prefix list, which of the entries in this table will be matched? The result is 192.168.10.0/24. Because the first 24 bits of the root network ID must be the same as those of 192.168.10, other bits can be different. And the prefix length must be 24. Okay, so the result is this. And next entry, IP prefix list Ruijie sequence 5 permit 192.168.0.0/16 AOE 24. So it represents that the first 16 bits must be 192.168, and the mask length is from 16 to 24. So the result is shown here. Right? And next IP prefix list Ruijie sequence 5 permit 192.168.0.0/16 GE 24. So the first part is very easy to understand. Right? First 16 bits must be 192.168. GE 24 means the mask length should greater equal than 24. So it could be 24, 5, 6, 7 until 38. It's from 24 to 38. So the result you can see is shown here. Right? Okay. This is about the configuration of prefix list. After knowing this, let's see. If we want to match all roots, it could be like this. Permit 0.0.0.0/0 less equal than 32. It represents any. Okay, it represents any. Or match the default roots. It's shown here. This is the default root. Match all host roots with 32 bits prefix length. so greater, equal than 32. And let's see, in this real case, how to use a prefix list to do the root redistribution control. Multiple static roots are configured on R1. You need to redistribute the static roots into OSPF and filter out the roots starting with 19168 and having a prefix length larger than 24. So we should configure IP prefix list first. So let's see it. IP prefix list deny 192.168.0.0/16 GE25. Since it's larger than 24, larger than 24 means 24 is not included. So during the configuration, we should use GE25. It's very important. And after that, for all the others should be permitted. So IP prefix list 1 permit. This is any, right? Any means for all the other entries. And then after configuring the IP prefix list, next is to configure the root map. The name of the root map is map1 permit 10. Match IP prefix list 1. So we are referring to the IP prefix list we just configured. And the last is to revoke the root map we just configured. So router OSPF1 redistribute static subnets. Root map1. So when we redistribute the roots from static to OSPF, we will check the routing entries based on root map 1 we just configured. Okay, this is the configuration of how to use prefix list to control the root redistribution. And the next, configuring a root map. The logic of a root map is as follows. Multiple root maps are executed in order of the sequence number. If a match entry refers to several objects in one entry, either of them should match. So this is a logical OR algorithm. If several match entries are present in a clause, OR must succeed for a given root in order for that root to match the clause. Okay. And if several set commands are present in a clause, they are executed at the same time. And it's the logical AND algorithm. Let's see an example. Root map Ruijie permits 10 match XYZ, set A, set B. Root map Ruijie permits 20 match P, match Q, set C, and root map Ruijie deny any. This command don't need to be configured because it's a default. It's system default configured. Well, what we should know is what's the relationship between XYZ, what's the relationship between set A, set B. You can see. Between X, Y, Z is a logical OR algorithm is applied. Logical OR means if you can match one of them, you are matched. And after you are matched, next set A and B. Set A, set B. The relationship is AND. Logical AND algorithm is applied. Means if you are matched, you should be operated by set A and set B. Okay, and next, match P, match Q is a logical AND algorithm. Means you should match P and Q at the same time. And then only after being matched by P and Q, you will be set C. You will operate the action set C. Okay. So about the root map, you must understand the relationship between them. Okay. So let's see the example here. During redistribution, change the magic value of some roots and ensure that each root has a different magic value. So you can see here. Now in OSPF, we have three. Right? We have three roots. And on R2, we should do the redistribution. So to set different metrics to them, you can see, we should have the ACO to match each root first, right? Because we should distinguish them. So we use ACO1 to match roots to 172.16.1.0 and 2.0. Then we use ACO2 to match routes to 172.16.3.0. And next, after matching these routes, next we configure the route map. The name is Ruijie, permit 10. Match IP address 1. Here 1 represents access list 1. Set metric 2. And if you match IP address 2, match ACO2, set metric 3. Right. And the router read redistribute OSPF route map Ruijie. When we do the route redistribution, we should work, or we should refer to the route map we just defined. So in this way, we can change the metric of them. So after that, you can see the result. For the first two routes, the metric is 2. For the last one, the metric is 3. Okay, next example, redistribute only some routes. For example, routes to 172.16.3.0 and 192.168.23.0 and filter out other routes. Okay, so let's see how to do that. Since we want to filter out some of the routes, so we should here use ACO to match them. Use ACO 1 to match both 1.0 and 2.0. Then use them in the route map. What we do here is deny. You can see it's deny. Match IP address 1 and route match. And route map Ruijie permit 20 set metric 2. So we will deny 172.16.1.0 and 2.0. They will not be routed to RIP. And for the others, we will change the metric to 2. The result is shown here, matrix 2, right? And these two routes are filtered by using route map. Of course, we should refer to this route map during the route redistribution. Okay, and the next, by default, hosts connected to R3 access the production server through R1. If R1 breaks down, data forwarding is switched over to R2. By default, hosts connect to R3, access the office server through R2, and if R2 breaks down, switch to R1. So in this case, we can use actually the route map to control the exit, right? So let's see how to do that. By default, the route to production server goes through R1, to office server goes through R2. It's configured by static route. While to do the maybe switch over, let's see what we configure here. Now, firstly, configure the static route first and use access list 1, access list 2 to match these routes. Then route map Ruijie permit 10 match IP address 1. If you match the first ACO, the metric is 10. If you match the second ACO, your metric is 20, right? And when we redistribute the static route into OSPF on R1, we use the route map we just defined, which name is Ruijie. So in this case, on R1, the routes matched by ACO1 will have a higher priority because the metric is 10. And the routes matched by ACO2 will have a lower priority because the metric is 20. I think the configuration on R2 is different. Let's see. You can see the static route configuration is the same. ACO configuration is the same. Which different is only here. On R2, we think that the routes matched by ACO1 has a lower priority, while matched by ACO2 has a higher priority. So in this case, R1 and R2, they can achieve a load balance, right? From R3 to production server by default goes through R1. To the office server by default goes through R2. And they will be the backup of each other. Okay, this is another application scenario of route map to control the exit. After knowing the configuration of it, next let's see some questions. First, the question, which of the following commands are correct about redistributing RIP routes into OSPF? A, redistribute RIP. B, redistribute RIP subnets. C, redistribute RIP subnets matrix 3. Which of them do you think are correct? I think it's B and C, right? B and C. And the next, what are the difference between prefix list and ACO? A, prefix list can be used to match while ACOs cannot. A, prefix list can be used to match masks while ACOs cannot. B, prefix lists can be used to match routes only. ACOs can be used to match both routes and data. C, both prefix lists and ACOs can be used to match masks. Prefix list has higher accuracy. So which of the following statements you think are correct? Here, B and C. Because ACO can also be used to match the mask, because we can use the extended ACO to control the mask. But it's not a currency, right? The mask must be the same. We cannot maybe have a control the mask length in a range, right? Must strictly match. Okay, so this is about the route redistribution and the route map. About this part, let's make a summary. The route redistribution allows both routers to exchange and advertise route information between routing protocols, thus connecting different routing domains. It's common that a network has multiple routing protocols because they have different application scale rules. And the route redistribution is typically used in the following scenarios, which we have mentioned in this course. And during the route redistribution, route maps filter routes or execute policies. And about the route map, especially you should know, you should be able to read and configure them to achieve different requirements. Okay, that's all for the route redistribution part. Thanks for your listening.